All right, so mass is the measure of inertia of an object. It's an SI system or an SI unit of kilograms. Now, mass is not weight, but in order to determine the weight of an object, you have to use mass times the acceleration due to gravity. So mass is a property of an object, and the weight is the force that's exerted by gravity. So if you're on the if you're on the moon has about 1/6 the gravitational acceleration of Earth. So if you were to take your mass, which is the same here as it is on the moon, and you multiply by 1/6, then your gravitational force will be 1/6. You will weigh less on the moon than you will on the Earth, not because you have less mass, but because the moon has less gravity. It has less gravitational force acting on you. You still have the same mass, but you would weigh less. And that's why if you ever see footage of people on the moon, they bounce around. The reason it looks like they bounce around so easily is because that there's less force for them to have to push their legs up so they can jump relatively high. Now there's two terms, gravitational mass and inertial mass. The interesting thing about these two terms is that this was one of the things that Einstein kind of he tried to figure out. Now you may look at this and it's like, well, why is one called gravitational, one's called inertia? Well, think back. Newton's second law is net force equals mass times acceleration. All right, that's usually referred to as inertial mass because if you apply a net force, that mass will accelerate. But then Newton came up with a gravitational force equation that also included mass. Now, these two equations are completely independent of each other. You didn't use one to figure out the other. However, this mass pops up in both equations. Now, Einstein, what he did is he tried to figure out, is there a difference between what the gravitational force calls mass and what Newton's second law calls mass? So what they did is he tried to come up with an experiment, any experiment he could possibly think of to say, all right, how do I test gravitational mass to see if that's different than inertial mass? And every single experiment over the past century has led scientists to believe that the inertial mass and the gravitational mass are the same mass. Now that's probably not news to you or anything. That's just something in physics we just said, yeah, mass is mass. But because those two equations are completely independent of each other and both of them have mass in it, there's a possibility that they're not the same mass. It's not actually measuring the same thing. So to test if you have a gravitational mass, you need to use the force of gravity. So an object that is falling or some sort of, you hold a spring and that spring has a gravitational force pulling on it, that would be a gravitational mass. But if you want to test if it's an inertial mass, what you do is you would basically push the object horizontally, balance out gravity so gravity is not affecting your experiment, and then and as you push the object, you apply a force and you measure the acceleration, and that gives you your inertial mass. Anyway, long story short, all these experiments trying to figure out if there's a difference between gravitational mass and inertial mass, and basically what we've come up with is they're the same mass. All right, so weight is the force that's exerted on the object that pulls downward. We've got the acceleration due to gravity is 9.8 meters per second squared. Gravitational force is equal to that mass times 9.8. We've done this many times, talked about the gravitational force of an object. Now, at the surface of the Earth, it's 9.8. If you go to the surface of the moon, it's 1/6 the gravitational acceleration. You can go to the surface and you can use that gravitational acceleration equation, gravitational constant times mass divided by the radius squared, and you can figure out the acceleration due to gravity on any planet just by knowing its mass and its radius. Plug those into the equation, you get your acceleration, and then you take your mass, multiply that by that acceleration, and you would figure out your weight on that new planet without actually going there. All right, so mass and weight, go ahead and answer this question. All right, so mass and weight, they are two different quantities. Mass and weight are two different quantities. And this is a huge thing that a lot of people still, even I could tell you to your face that mass and weight are not the same thing, but still people will believe that they are the same thing just because we use them interchangeably every day, but they're really not. You can be without weight, but still have mass, because weight is a gravitational force being applied to you. So if you don't have a force of gravity on you, you're weightless, but you still have a mass. All right, next one, it says a stone is thrown straight up at the top of its path. The net force acting on it is what? And quite simply, the force of gravity is applying to it, whether it's sitting on the ground or if it's up in the air. Gravity's still pulling on it, so it's going to be equal to its weight. It's going to be equal to its weight. All right, so whenever one object exerts a force on the second object exerts a force back. So this is Newton's third law, right? So every force has an equal and opposite force. So force of this block as it's pushing down on the table is going to be equal to the table as it's pushing up on the block. And we call this force 1 and force 2, but both of those are going to be equal in magnitude, but opposite in direction. Equal in magnitude, but opposite in direction. So if, let's say, the table's pushing up with 10 newtons, then the box is pushing down on the table with negative 10 newtons. Now, if you ever want an easy way to figure out what the equal and opposite force is between two objects, first of all, you figure out what force is being applied. So let's say you have the box and the table. The box is applying a force on the table. So to figure out Newton's third law, the equal and opposite force, you literally take those two objects and you flip them. So if the box is pushing on the table is pushing on the box. If ever you need to figure out what the equal and opposite force is, it's that simple. You take the two objects that is being applied between and you switch them. So let's say it's something like you have a force of gravity on you. All right, so gravity is pulling on my body, pulling on me. So you may think, well, what's the equal and opposite force there? Well, gravity is being caused by something. Gravity doesn't just exist. Something has that gravitational force on. If you think about it, it's the planet Earth, right? So Earth is pulling on me with, let's say it's 1,500 newtons. If Earth is pulling on me with 1,500 newtons, what does Newton's third law say about me pulling on the Earth? I'm also pulling on the Earth with 1,500 newtons. All right, so this is referred to sometimes as action-reaction forces. I don't really like the term action-reaction simply because action-reaction implies that this happens and then this other thing happens. When in fact, these two forces, one force doesn't happen and then the other force happens after it. These two forces exist simultaneously. As soon as the box touches the table is touching the box. So I would call it more of action-action forces. But it's called action-reaction simply because over years and years of referring to it, that's kind of the name that has stuck. All right, so an object at rest must have zero net force. If it's sitting on a table, the object exerts a downward force with mass times gravity. That's because gravity's pulling down. And then you got the normal force up. The surface of the table exerts an upward force on the block that's normal. And it is exactly as large as what's needed to balance the force from the object. So what about this? What about this? Is this Newton's third law? I have a downward force on the box, and then I have an upward force on the box. Both of those are equal and opposite. Equal and opposite. So it sounds like Newton's third law. The only problem is, if you remember, Newton's third law is only between two objects. It's only between two objects. So let's look at this. The force of gravity is between the box and the Earth. And then the normal force is between the box and the table. That's three objects. So when you're talking about more than two objects, you're not talking about Newton's third law anymore. So this one specifically, you're talking about a system, which is our box, and two things applying a force to that system. That's the table upward and Earth pulling downward. So this is not referring to Newton's third law of equal and opposite forces. This is more so referring to what we call balanced forces. This is more of Newton's second law. Newton's second law says that when all the forces acting on a system, on an object, is zero, then they are balanced. There's no acceleration. But think about this. Another way of thinking about Newton's third law is if I remove one force, does that remove the other? If I were to take this table and just completely pull it out really quickly from underneath that block, would it make it move? Would the other force of gravity, with the force of gravity, would that disappear? And of course it doesn't. All right, gravity still pulls down on it, right? Gravity still pulls down on it, which means that those two forces are not Newton's third law. All right. So the net force in the y direction equals 0. That's Newton's second law. So normal force is going to be equal to that force of gravity. All right, so this next one says an upward force of m is applied to the block. Magnitude of the normal force is going to be equal to the, well, in this instance, let's say we have another force, right? We got a force that's pulling upward. And then we have a normal force with a table. So think about this. Is the normal force going to be more, less, or equal to the weight of the object? Is it going to be more, less, or equal? Well, if we use Newton's second law where the net force is equal to 0, then we have an upward force of normal force. We got this upward force of F, so somebody's pulling up on it, but gravity's still downward. It's negative mg. So if you figure out the normal force, what you're going to get is you're going to get mass times gravity minus that force. So what does that say about the normal force? It says the normal force will decrease. The normal force is going to decrease in this instance. What about this one? What if we apply a downward force? So somebody's pushing down on it. As somebody's pushing down on it and the normal force is pulling up on it, what's going to happen to the normal force in this instance? What happens to the normal force here? Well, if you do your Newton's second law, net force equals mass times acceleration, the acceleration is 0. You get normal force that is upward, the weight is downward, and then you get this force downward. You take those to the other side, and you see your normal force is actually going to increase. Your normal force is going to increase. It's going to be larger. Now, if you think about vector addition on this, right? You take this vector, which represents its weight, this vector, which represents its force, those two together will be one large vector downward, and then the normal force to balance needs to be the same amount upward. So it's those two vectors put together, normal force will be that much upward. All right, and this one it says action-reaction forces. What's the answer going to be? All right, action-reaction forces. They always act on different objects. So if I have one force acting on an object and a separate force acting on the same object, and I'm talking about Newton's second law, net force equals mass times acceleration. But if I have a box applied to a table and a table applied to the box, it's always applied to different objects. Next one says 20-ton truck collides with a 1,500-pound car and causes a lot of damage to the car. Since a lot of damage was done in the car, what's going to be the answer to this one? All right, so if you're thinking about Newton's third law, even though there's a lot of damage to the car, it still applies an equal and opposite force. So let's say you got a bug that splatters on the windshield of a truck as it's going by. All right, that bug that splatters, what happens to the force on the truck? What happens to the force on the bug? Those are going to be equal and opposite. Now, with that being equal and opposite, a small force acting on a bug obviously is going to make it splatter, but a small force acting on a truck is not going to affect it at all. But it's still the same force acting on both objects. So a golf club hits a golf ball with a force of 2,400 newtons. The force on the golf ball exerted on the club is what? All right, so realize we have two separate objects, the golf club and the golf ball. So the golf club on the golf ball is 2,400 newtons. Now it's saying the golf ball on the club. What is that going to be? Well, it's going to be exactly 2,400 newtons because that's equal and opposite. It's Newton's third law. All right, this example says a block is a mass m moving at a speed of v naught from rest with a constant force. All right, so we apply a force that's actually going to be in the opposite direction from the velocity. Now, if you remember, net force is the same direction as the acceleration. And whenever you have an acceleration and a velocity that are in opposite directions, then you're going to slow down. All right, so in this instance, we're going to slow down. We're going to use Newton's second law, net force equals mass times acceleration. Now, they already put F in there, but really it's net force, summation of forces. But since there's only one force that's being applied in the x direction, we'll just call it F. All right, so to figure out what that, let's see, what that displacement is going to be, we're going to rearrange this equation to solve for that acceleration and then plug that into here. Our initial velocity is going to be 20. Our final velocity is going to be 0, so that part's going to go away. So we take this to the other side, divide by 2 times acceleration. I'm sorry, divide by 2 times displacement, and that's we're going to plug that into the equation over here. And that gives us our equation there. All right, now to solve for our displacement, we're going to take the displacement to the other side, divide by force. And remember that negative is in there simply because the force is in the opposite direction, so that negative actually pops up right there. Okay, so you plug all that in, you get 100 meters. 100 meters. All right, so 100 meters for your displacement. All right, so what about this two-block system? Let's find the acceleration of this two-block system. All right, so the first thing we're going to do is we're going to set up a free body diagram of both of these. All right, so let's look at the forces that are acting on mass 1. It's got a downward force of gravity. It's got an upward force of normal force. Now, in this instance, those two forces are going to be balancing each other, so we really don't have to worry about those. We can basically just ignore the y direction. However, we are going to have a force of tension that's forward. All right, so net force in the y direction is 0. That means normal force is going to be equal to force of gravity. Nothing too surprising there. In the x direction, we are going to have an acceleration, right? This string is going to pull on that object and make it come forward to the pulley. But the only force acting on it is going to be the force of tension. So tension we don't know, and acceleration we don't know. So this equation has two unknowns. All right, so let's look at the second mass. So it has a downward force of gravity, and it also has an upward force of tension. Okay, now these two forces of tension will be the same only under a certain couple of circumstances. Number one, this pulley needs to have very, very, very little friction. Very little friction. Also, this pulley cannot have a lot of mass. Something we're going to be getting into later is what's called rotational inertia. And if this thing is rotating, then that means one of these two forces, one of these two tensions have to be bigger than the other in order to produce what we call a torque, to produce rotation. However, if we assume that that pulley just doesn't have a lot of mass, doesn't have a lot of rotational inertia, and we can kind of ignore the fact that it takes a torque in order to rotate it, then we can go ahead and say that these two tensions are going to be equal. Now in class, we're going to use pulleys that have very, very low friction and are very, very light so that their rotational inertia is very small, and effectively these two tensions will be the same. So we don't have to worry about that pulley too much. Anyway, so if we use Newton's second law for this, we're going to say that the acceleration is in the negative direction, but since acceleration is down, you know what? Let's make downward positive. All right, let's make downward positive. So downward being positive, that means the force of gravity is going to be positive and tension is going to be negative. So force of gravity positive, tension negative, and then mass times acceleration. One good practice that we usually do when we do Newton's second law is we always make the direction of the acceleration positive, which makes this side of the equation always positive. And then we just change the direction of the of the forces to accommodate. All right, so we plug this in, we isolate our tension, right? But then we have acceleration again. So basically we have another equation with two unknowns, tension and acceleration. All right, so we have a system of equations, right? System of equations where tension is equal to mass 1 times acceleration, but tension is also equal to mass 2 times gravity minus mass 2 times acceleration. So what we're going to do is we're going to combine these two equations, all right, set them equal to each other, and then we're going to isolate our acceleration. So we got to get this term with acceleration over to the other side, which means we're going to have mass 1 times acceleration plus mass 2 times acceleration. We isolate that acceleration by factoring it out, so it would be mass 1 plus mass 2. All right, so we bring this over to the other side, becomes positive. Factor out acceleration, we'll have mass 1 plus mass 2. So then when we take mass 2 times gravity, divide by that mass 1 plus mass 2, this is going to be our acceleration. So in this example, we make a lot of assumptions, to be quite honest. We also assume there's no friction with this surface right here, all right, because that would be another force we would have to include with this and make it more complicated. We assume that the pulley doesn't have much rotational inertia, and with those assumptions, we get that our acceleration is going to be equal to the mass of this hanging mass. So it's going to be the force of gravity of this hanging mass divided by the total mass of the system, and that'll give us our acceleration. Okay.